I'm going to okay. Ooh. Uh-oh. All right. Got an echo going somewhere. Is that gone? Okay, echo's gone. All right. Sorry about the delay. I don't know what the deal was. Yeah, OBS didn't want to work this morning. So let us hop on in. Today I want to talk about two types of graphs that are relevant for energy. And then, where's my pen? Fancy pen. And then we're going to start talking about chapter 12. And chapter 12 is the last chapter. Yay! So we're almost there. So I'm sure you're all very excited. So we have been talking about energy. Ooh. Specifically, we've been talking about, hello people on Twitch. Sorry about the delay. I don't know what was wrong with OBS. It didn't want to connect to Twitch today. But I fixed it. Yay. So tell me some of the types of energy that we've been talking about. Actually, let me pull up the chat over here. There we go. What are some types of energy that we've been talking about? Okay, we've definitely been talking about kinetic energy. That's our energy due to motion. Okay. Potential energy, we've talked about two types of potential energy so far. We talked about gravity and springs. There's also things like chemical energy, but we have not really talked about it. Heat, definitely. Yep. Energy to deformation, right? I'm going to call this like thermal energy. This is our catch-all term for loss to things like heat, friction, heat, sound, etc. Dissipative forces. Okay. We talked about loss to deformation. Okay. Good. Okay. So I want to take a couple minutes to talk a little bit more about potential energy. So remember that potential energy was U. And so our change in potential energy was equal to the negative work done. Change in potential energy was equal to the negative work done by a conservative force, right? So things like springs. So if I take we haven't really talked about pendulums yet. So let's say I have a pendulum. I have a box or block on a string, okay? And I pull it back to say right here. Oh, that's definitely not what it looks like. Okay. Some angle theta. Okay. So let's say we know mass. Let's say we know theta. Can you tell me how much work did we do to pull out that mass from vertical to some angle theta? Don't have any ideas? I asked you how much work we do, so that's kind of strange. Um, no thoughts? Okay. Eden suggests on Twitch finding the change in potential energy. That seems like a great plan. Okay, so here's my pendulum. Okay, so I have pulled it from here to here. Lovely. Okay, so what was my initial? Also, be careful, Eden. You want to do delta U is always final minus initial. Okay, so what was our initial potential energy? U initial equals what? Gonna sneeze. Uh-huh. So, because it's tied to a rope, why would it be more? Thank you. Because it's tied to a rope. Gracias. Okay. So that's a really interesting point. So John said that it's tied to a rope. So if we were to cut the rope, it would fall. And so it must have some potential energy. Now, that is a really good point. But we don't know where the ground is, right? So we have our thing and we could cut the rope, and maybe the ground is like right here. Maybe the ground is way down here, right? So it's hard for us to say how much potential energy that it has at this point. So one thing to remember is that we get to decide where zero is, right? So I can declare that this is my potential energy equals zero location. You're like, okay, but what if it falls down here, right? It would be losing potential energy. That's totally fine. Negative potential energy is totally allowed. It's a very technical term, totally allowed. So it doesn't matter. What matters is the change in potential energy. So if it is positive, that means it is gaining potential energy. If it's negative, that means it's losing potential energy. So usually this means it's slowing down. Usually this means it's speeding up because the energy is coming to or from kinetic. So yeah, we don't actually care if the potential energy is negative. So we could say U equals 0 here, and we cut the rope and it falls to the ground, and U is negative 100 joules. Well, my delta U would be negative 100 minus 0. I have lost 100 joules of potential energy, so I have gained 100 joules of kinetic energy. I just keep going with my problem. Does this all make sense? So because I get to decide where 0 is, I'm going to be very lazy. I'm going to decide that the starting point is 0. Because I said so. Right? This is just like when you're doing like, oh, it's a car driving along. Where is x equals 0? X equals 0 is wherever I decide it is. I'm the boss. Okay, because I said so. So this is 0 joules. Okay. What about my final potential energy? How can I find my final potential energy? We need the final height of the box, yes. Right, so remember we can say our potential energy is mgy. So we can say this is y equals 0. We need to know this y. Okay, so I'm going to help y'all out here with some geometry. So if this is y equals 0, we want to know this y. I'm going to draw a line here to make this a triangle. Okay, right. So this is our height, our final height. This is our box. This is our angle theta. Okay. And this is the length of our string. The string's length isn't changing. So this is also L. Okay. So now I'm going to do h sine theta, cosine theta, 0.8. Maybe. Not sure about that one, John. So I know my y is sort of this y. Okay. So this piece here is the side of a right triangle. So if this side is L, this side is theta, then the green part is going to be, let's see, cosine theta is going to be adjacent, which I'm going to call, what am I going to call that? I'm just going to call it adjacent, divided by hypotenuse. My hypotenuse is L, right? So I know this adjacent piece adjacent is L cosine theta. So my y, I'm really going for my color coding today, is L, so it's this whole piece, minus just this piece, which is L cosine theta. Yeah. Yeah, there we go. L minus y, L minus y, L minus L cosine theta. Yeah. Okay. So my U final is mg times L minus L cosine theta, which I can substitute as mgl 1 minus cosine theta. Can you hear the Carolina wren outside my window? Very cute. Okay. So put this in here, mgl 1 minus cosine theta. Okay. Making sense. All good. So let's say it had a mass of 1 kilogram. Let's say the length of the string is 20 centimeters. And let's say we pull it back to an angle of 15 degrees. Okay. So what is the change in potential energy? That would just be mgl 1 minus cosine theta. So 1 kilogram times 9.8 meters per second squared times 20 centimeters, which is 0.2 meters, times 1 minus cosine of 15 degrees. Okay, let's do a little bit of, where did the L cosine theta? It came from this triangle. That's a right triangle where the hypotenuse is the length of your string. L cosine theta is like the vertical distance from the apex to the height of the thing. So the height of the thing from its starting point is the length of the string minus that chunk. Okay. 9.8 times, 9.8 times 0.2 times, that's not what I should have done. I should have done cosine 15. Negative plus 1. Okay, so it's only gone about 3 centimeters up. It's not very big. Oops. Times 0.2, actually not even. It's gone 0.6 centimeters up. Times 9.8, I get 0.067 joules. It's all right. Seems pretty low. 15 degrees is not very much. Yeah. 0.067. Okay. So that is how much potential energy we gave to the thing by pulling it this angle. Okay. So how much work did gravity do while we pulled it back? Okay, I have one thought from Twitch. Anybody on Teams? No. Actually, I have a fair number of people on Teams. That's good. But nobody has any thoughts. Nope. All right, well, John, you were correct. Negative 0.067 joules. right? Because, yeah, work done is the negative change in potential energy, right? Which should make sense. The work done would be the force of gravity is downward, but we're moving it from here to here. So if we did that whole integral, we should get a negative number because gravity is working against the motion, so it is doing negative work. Okay. Sort of a pointless diagram right there. How much work did we do? So that was our original question. How much work did we do to pull that mass out? So this is one where students intuitively are like, okay, work is force times distance times cosine theta, but I don't know the force. I don't know. I guess the distance is this arc. I don't know. Theta's changing all the time. This is really difficult. But there is an easier way. And John and some folks in Twitch teams, nobody's really got a thought, but Twitch is killing it. Yep. Positive 0.067. How did y'all know that? Why is that the value? Why? Zero kinetic energy change, so our network must be zero. So that must be the sum of the work done by all the forces. Us. So it has to cancel out. Good. Excellent. Okay. So this is all good so far. What happens? So that's sort of the end of that question. Good job, check. What happens when you let go, or when we let go? Turns into kinetic energy. Yep. U turns into K. Okay. Where will the box be moving the fastest? At the bottom. Yep. People on Teams, I'm a little concerned that nobody's got any thoughts. Twitch is killing it here. Okay. The bottom. Okay. So that would be the point where K is maximum, U is minimum. Okay. You're just a little tired. I feel that. Absolutely. Okay. What about in between? Let's say at half the angle. Is it going to be half the speed? Can non-conservative forces allow things to get potential energy? No. So John asked a good question. Twitch, can non-conservative forces allow things to get potential energy? No, because that is the definition of a conservative force. So in order for it to have potential energy, it has to be a conservative force. Yeah. Yep. Good question. So what I'm going to do is I'm going to draw a graph. where this is theta, and this is potential energy. So when theta is 0, my potential energy is 0. What's my graph going to look like? It's going to look like U equals some stuff times 1 minus cosine theta. Okay, what does cosine theta look like? Okay, cosine theta looks like, pretend that's a, whoop, didn't mean to do that. Pretend I can draw graphs, right? That's what cosine theta looks like. So 1 minus cosine theta. So this is 1. This is -1. This is 0. So this point is going to go to 0. This point is going to go to 1, or whatever our constant is. So it's going to look like just this part, right? So this section flipped over, right? And this would be this degree where cosine is 0. This would be 90 degrees. Negative 90 degrees. Okay. Is this making sense? So this is theta. That's our angle. Yes. Okie dokie, great. Okay, so, but ours, we didn't pull it all the way back to 90. We only pulled it back to 15. So what I'm going to do is draw a line saying, okay, we pull it back to, I know this is not to scale. Let me move that a little bit. So it would be more like right here, 15 degrees. We can zoom in a little bit here. Okay. So this line that I have drawn, this is my total energy line. Total energy. Okay, so this is telling me basically the energy that it has to start with, right? It starts off with U equals 0.067 joules, okay? As it swings down, as our angle changes, our potential energy, right? Our potential energy is this height, U. Our potential energy is going down. Our total energy stays the same. So the difference between the energy I started with and the potential energy that I have at some given angle is the kinetic energy. And I have my maximum kinetic energy at the bottom, like we expected. Kinetic energy gets less as our potential energy gets bigger. Any sense? All good. Woo. Okie dokie. So another kind of thing that it might look like, if we have our right? If we start pulled out to a higher angle, that would be our new total energy line, where this is the angle, how far we pulled it out, right? So what angle is it going to swing out to on the other side? If I pull it to, let's say this is 70 degrees, how far will it swing on the other side? $70, yep. It's going to swing down, swing back up, swing down, swing back up, swing down, swing back up, swing down, swing back up. Okay, what is happening at this intersection? Where our potential energy meets our kinetic energy. Runs out of kinetic energy and stops. Does it just freeze? It goes swing. It just stops here, changes direction, right? Swings out, and comes back. So this is what is called a turning point. Turning point. So this is something I'll expect you to be able to do to identify the turning point. It's easy, it's just the point where it intersects. This is also a turning point out here. Turning point. Okay. All right, making sense so far? All good? Wouldn't the middle be a turning point? So that is an interesting question. So the middle is kind of a turning point in terms of it was going down and now it's going up. But its turning point means V equals 0 and it reverses direction. So it is technically a turning point for your y direction, but not for your overall motion. Does that make sense? That's an interesting point. It does have something special happening there, but not necessarily because the potential energy is 0. Yeah. Okay. Turning points. All right. So here's a situation. Let's say we have our pendulum. Pendulum is just sitting at rest. This is U, this is theta. So we have our pendulum. This is my high quality pendulum demo here, right? So currently our potential energy is 0. Our total energy is just here. This is what we call an equilibrium point. It's not doing anything, right? Equilibrium. We're going to talk more about that in a second. But what if I smack it and give it some amount of energy? No pen. Pen doesn't like it. Oh, I forgot to record. Oh no. Crap. That's okay. I smack it and give it 0.09 joules of energy. What happens? Well, now my total energy line is going to be my starting point plus the amount of kinetic energy that I gave it, 0.09. So my total energy line is actually here. So what's it going to do? Is it going to stay at theta equals 0? It's going to go in the direction I smacked it. True. Is it going to swing all the way out to 90 degrees? Is it going to swing past 90 degrees? Is it going to swing out just a little bit? How far is it going to swing out? Depends on how much you smack it. How much I smack it determines the height of this total energy line. So it's going to swing out until all of that kinetic energy turns into potential energy, and kinetic energy is 0 at the turning point. So it's whatever value theta where our u is equal to 0.09. The turning points will change position, exactly. The harder I smack it, the higher my total energy line is going to be, the greater the theta is where it's going to swing out. Okay, making sense? So our total energy line is our starting potential energy and our starting kinetic energy, right? So if our, oh no, I undid my, let me fix. We're going to do a different knot this time. How about button hitch? Okay. Ah. Sorry, I undid my. So Cole asked, how many joules does it take to go past the turning point? The turning point is by definition the point where it runs out of energy. So I don't know Palomar knot. I'll have to look that up. Monkey fist, nobody's got time for that. So there we go. That's better. What was I saying? Yeah, so basically what happens when you increase the energy is you're increasing the theta for the turning point. At a certain point, it's going to swing up past horizontal, and then you have sort of other stuff to worry about, right? See, it kind of flops when it gets that high. You have to spin it a lot harder. Your tension becomes weird. So we're basically going to ignore that situation. Okay. But say I pull it out this far, and then instead of just dropping it, I push it, right? So if you just drop it, if I pull it out to 10 degrees and let go, it's going to swing out to 10 degrees on the other side. If I pull it out to 10 degrees and push it, it's going to swing out further than that because my starting, that was weird. My starting point was here, but my total energy was here. So it's going to swing down and then up further, out further, out further, out further, right? So this is K initial, this is U initial. Okay. This making sense? Can't you tell me what a Palomar knot is? I want to learn it now. My favorite knot is the Alpine butterfly. Okay. So far we've been doing it specifically for this graph. You can do this for any potential energy graph. So let's say you have X. This might be something like a roller coaster, right? Yes, you're correct, John. Yep. And Chris, you would add the energy of gravity and the energy that you use to push it. Mm-hmm. exactly. So I have however much potential energy due to how far I pull it back, mg L1 minus cosine theta, and then some amount of kinetic energy. So this comes from the work I do to push it. Okay. So this could be just like a hill. This is like a hilly landscape. Hill landscape, right? And you are longboarding. So let's say you start right here. You start and you just step onto your longboard at that location. What's going to happen? You step on. This is potential energy. It's also essentially just the height graph. You going down. Yep. So you will move in the negative x direction. And how far will you go on the other side? John has pointed out you will end up at the point at the same height to your left. So this is your total energy line. So this point right here will be your turning point on the other side. So you will go zooming down and you'll go up, 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 slow to a stop, and then roll back down and then come right back up to where you started. Presuming there's no friction, you're correct. Okay. All this making sense? All right. What if you start at but you kick off? You don't just step with some initial energy. You kick off, you start with some initial energy. So let's say you start off with just a little bit. So this is plus kick. Okay. This is your new total energy line. Okay, your total energy is going to be higher. Depends on the magnitude and direction of your kick, yeah. So you're going to go down. You're going to go down, going faster, faster. Where are you going the fastest? At the bottom, yep. Okay, so you're going the fastest down here. You slow down, you slow down, slow down, you slow down. Are you going to stop at this same turning point? Yeah, good. You're going to lowest. No, you're going to keep going to your new point right here. Okay, then what? So it is possible that you have precisely enough energy such that your K equals 0 right there. So if your energy exceeds it, so this is your total energy, you will still have some amount of kinetic energy. You go over the hill, right? If your total energy is not enough, you come up and you slide back. Right, we're having some trouble here with the pen. There we go. Don't know why it does that. Slide up, slide back. Slide back. This would be a turning point. But what happens if it just sort of kisses right here? So right at the top of the hill, you have precisely 0 kinetic energy. What happens? Stop moving. You just and then you're stuck. So this is what is called any point where it flattens out, right? It's called an equilibrium point, where it is possible to stop if your total energy equals your potential energy. If your total energy is too big, you'll go over. If it's too small, you'll slide back. But if it's just right, you can stop and just chill out there, right? You chill at the top, yeah. This is where your tangent line is horizontal. So equilibrium happens when your tangent line is horizontal. Okay. So can we say tangent line is horizontal in a mathematical way? How do we say tangent line is horizontal? Derivative is 0. Derivative of u in the x direction is 0. Okay. So I want to add, there's one equilibrium point right here. Can you find any other equilibrium points? There's probably one right here. There's probably one right here. Looks like there might be one right here, maybe. There's definitely one right here. Right, those are all our equilibrium points. Yep, bottom of the hill for sure. What's the difference between the top of the hill and the bottom of the hill in terms of being an equilibrium point? So the top of the hill is what we call an unstable equilibrium point, right? If you breathe, if you sneeze and add even a tiny bit of energy, you're going to go over, right? That is an unstable equilibrium point. It's going to go meow, right? The bottom of the hill, if this is where your total energy is, you are just sitting on your longboard at the bottom of a hill. Maybe you sneeze, maybe you kick a little bit. You're just going to rotate around that bottom point. This is a stable equilibrium point. A little bit of disruption, you're just going to kind of oscillate around where you are. Up here, if there's a little bit of disruption, you're going to zoom away on a new adventure, right? So it's not so much about your absolute k equals 0, u equals 0. It's about concave up versus concave up versus concave down, right? You are unstable balanced here, but you're stable balanced here. Zoom, yes, very important. This is taking longer than I thought, but this is actually really important for physics too. So, okay. All right, let me ask you another question. Where will your acceleration be the greatest magnitude? So we're not going to worry about positive and negative, but just where do you have the biggest change in your speed? Is it going to happen at the bottom? Is it going to happen at the top? Is it going to happen like here at the turning point? Is it going to happen right here? So not at the stable equilibrium point. In fact, the opposite. So if you think about a hill, right? You know, what is the scariest part of this hill? Is this scary? Or is this scary? This is way scarier because it's steeper. So Andrew says about 20% of the way through. It's kind of hard to see on this graph. I realize that this is not something that's ideal for asking you. But I would say like probably here, yeah. Steepest equals scariest. Scariest equals greatest acceleration equals the greatest net force highest absolute value of the derivative. Yep. So where we're going with this is that the force is essentially the derivative of your potential energy graph. So when your tangent line is horizontal, that means there's no force. That's what an equilibrium point means. When your graph is really steep, you have a heck of a lot of force, right? And this makes sense because delta U equals work done, but our work done is the integral of force over distance. So our force is the derivative of, and there's a negative sign wandering around, but I'm going to ignore it. Absolute values for everyone. All good, making sense. This took a lot longer than I hoped it would, but it's important for physics too. Okay. All right. So I said I was going to talk about one other type of graph. We're not going to get to center of mass today, I don't think. I'm sorry. Another type of graph. I might make a little center of mass video or something. Another type of graph. So we remember this. Yes, we all remember this. I'm going to do some toying around with this equation. So the net force is what happens if you add up the work done by all of our forces, right? However many there are. Okay. I can divide these into categories. I can say work done by conservative forces. So this is like gravity, a spring, things like that. Okay. I can say work done by dissipative forces. This is things like friction. Friction. I can say work done by external forces. So this is things like a push or pull, or like wind, or like a normal force would be like this for things like person in an elevator, right? Every force will fall into one of these categories. Okay. Hopefully that's making sense. Okay. I know that the work done by a conservative force is the negative change in potential energy. Okay. If we have no friction and no external forces, we have negative delta U equals delta K. We can say 0 equals delta U plus delta K. This is energy conservation. Energy conservation. But that's only if there's no friction and no external forces. Okay. If I do have friction and external forces, this would become delta E system is delta U plus delta K, right? If not conserved. Okay. Let's keep looking at our general case. General case. Negative delta U plus work done by dissipative forces plus work done by external forces equals delta K. Okay. The work done by a dissipative force is pretty much always negative. Right? It's always taking energy out of your system. Not 100% of the time, but like almost always. And if it's not, you'd usually consider it an external force anyway. So this means that a negative amount of work done by a dissipative force means I have a positive increase in my thermal energy. I know I've talked about this before, but it was just sort of in passing, right? So friction did negative work. It took energy out of our system. Where did that go? It went into thermal energy. Okay, so I can put that into my equation. Negative delta U minus delta E thermal plus external work equals delta K. Okay. Now I'm going to rearrange it. Stick with me. This is fine. Okay. Work external equals delta K plus delta U plus delta E thermal. Delta K is final minus initial. Delta U is final minus initial. You don't have to remember this, but it helps you to know how these equations work together. Then I'm going to move this to the other side, and I'm going to move this to the other side. So I have my initial potential energy, my initial kinetic energy, plus my external work equals my final potential energy plus my final kinetic energy plus my loss to friction. I think of this as sort of my input and my output for some situation. I start out with, say, a skateboarder at some initial height with some initial speed, and he's got a sail on his skateboard, so there's external work pushing him, right? So we have some starting UI, some starting KI, and then external work pushing him. And then at the end, which might be some random position, he will have some final potential energy, some final kinetic energy, and then whatever extra stuff got lost, the friction along the way. Is this making some sense? Hopefully. So I like to use this, or people in general like to use this to create bar charts. Bar charts. So a bar chart is like I have an axis. So this is my 0 axis. And then I have sort of a bar for initial potential energy, initial kinetic energy, work external. And if I add these together, it should equal my final potential energy, my final kinetic energy, my loss to friction. So in our example with a long border, so let's say he starts here and he kicks off with some energy. So he starts with some potential energy. He starts with some kinetic energy. Let's say there's no sail, no external work. Delta ETH is change in thermal energy. You can think of this as loss to heat or change in thermal energy. Okay. And then he ends up right here, let's say. So if this is his ending point, he has less potential energy. He's maybe lost a little bit to friction. And then whatever's left, like let's say this is 10 joules, this is 5 joules. So he starts out with 15 joules of energy. At this ending point, he has 3 joules of potential energy. He lost 3 joules to friction. How much kinetic energy does he have? This must be 9 joules. So he must be going faster than he was at the start. Does this make some sense? So I can do some more sort of examples here. New initial, K initial, work external, plus U final, K final, delta E, TH. So let's say I'm going to do green, lifting a beam with a crane with increasing, let's say, decreasing speed. What would the energy bar chart look like for this case? Okay, well, we have a beam. Maybe it has some starting height, but we're lifting it upward, so its ending height is going to be higher. So it has gained potential energy. Decreasing speed means it had some speed, but then over time it's going to be going slower. Okay. Generally, there's no friction in a case like this. So we must have done, in order to make these balance, we probably did a little bit of external work to lift it upward in order to make it balance. Does this make sense? Yes, no? Okay. Let's do, okay. There's a question on your homework where it is Sam skis down a hill with wind in his face, but no friction. and increasing speed. Okay, what is his bar chart going to look like? Well, he's going down a hill, so he must have more potential energy at the start than he did at the end. There's no friction, so he has increasing speed. So his kinetic energy is some amount to start with, and then that gets higher. All right. A wind in his face. How do I represent the wind in his face? Through external work, yeah. I'm going to make this a little smaller. He's pretty much at the bottom. Okay. What's the difference between wind behind him and wind in his face? Resistance, wind in his face is pushing against his motion, the direction, okay? So how do I draw that on my bar chart? Okay, wind behind versus wind in his face are opposite directions. One is helping him, one works against him. So negative versus positive, okay? So it would be negative work. If the wind was from behind him, it would be positive work. So how do I draw it on my bar chart? Negative. Okay, negative. Okay. Making sense? Yeah? Okay. All right, let me draw one and then you can tell me what you think. Give me an example of a situation that it would represent. And you'll get different ones, so they don't all have to be the same. Okay, let's do one more. Let's say, I'll do blue. I'll do blue. Actually, no, I want this one. Blue. Okay. So I'm going to give you some friction this time. That's too big. Okay. So in the chat, write me an example of a situation where this is external work. This is the correct energy bar chart. So the way to think about this, I tend to handle it in pieces. I think about potential energy. Is it starting higher or lower? I think about kinetic. Is it going faster or slower? I think about friction and work. Is there friction? Is there work? Okay. Rolling down a rocky volcano. Tell me how the volcano plays into this. It doesn't. Okay. So, okay, how does the external work? What is doing the external work in that case, Eden? Okay, so Shannon says going down a slope with friction. Okay, the external work for your case as well, Shannon. So, can I move this? I'm gonna move this. Yes, I can. Wow, that's so fancy. Okay. So we can have rolling down hill or slope. Friction. But what about external work? Biking down a steep hill during a windy day. So that's one possibility. So we could have external could be wind in your face. That's definitely a possibility. No, so friction would still be negative because your motion is down the hill, but friction is working against you. If there were no friction, this would be almost like friction in your bike ears. It would be slowing you down. So rolling is a little challenging. So I would think about it more in terms of like a box sliding down a hill, maybe, or somebody skiing down a hill. Friction, good question. Does friction count as external work? No, because we have put friction out here separately. You only want to count everything once. So it's either external work or friction. It can't be, or thermal. It can't be both. Same with gravity. Gravity can be either potential energy or external work. It can't be both. Can't double count. So I might say a box that is on a rope, box being lowered down a ramp. With friction and increasing speed, right? Because the rope is doing negative work, it's against the direction that the thing is going, right? This might also be sort of, you could do like a person in an elevator, right? Elevator's going down, it's speeding up. There's some friction slowing you down, but also there's hopefully cable in your elevator slowing you down, right? Does this all make some sense? Hopefully, yes. Okay. Yep. Awesome. Okay, we did not get to chapter 12 yet, which is not great. What I might try to do is, can I do chapter 12 in 2 classes? I think I can do most of it. I might, yeah. I think so. I think we don't generally get that far. I think it's okay. Yeah, 2 classes. We'll live. Okay, let's stop there. Thank you all so much for your time and attention. I appreciate it. And I will see y'all on Wednesday for your test. Okay, good question. What chapters are being covered on the exam? Chapters 8, 9, and 11. So 10 is energy, which is what we've been doing the last couple days. That is not on the exam. So I should be careful. So chapter 8 is circular dynamics. Hopefully you saw my announcement about that. We had an argument about this because it was supposed to be on the midterm, and I told y'all it would be on the midterm, but then they didn't ask any questions on the midterm, so they decided to put it on this test. Like, yeah, but I told you it was going to be on the midterm. So I apologize about that. 9 is work and kinetic energy. We actually did 11 first, which was impulse, momentum, and collisions. This is because the third edition of the book does it in this other order, and I like that order better, so I'm not changing it because they changed the edition of the book. And then 10 is sort of potential energy, springs, stuff like that. There is a practice quiz. Can you all see the practice quiz? That has sort of more questions, and then there's also kind of the homework. Okay, good. I definitely recommend doing these two. I went through the practice quiz and tried to cut out everything that is not like everything from chapter 10, so it should just be these chapters. Yes, chapter 10 is not on the exam, and it is not a common exam, so if they try to put chapter 10 on it, I'm going to take it off. So, yeah. I'm always behind, and I realize I'm always behind, but my students always do well on the final exam anyway, so. Okay. Yes, I have office hours today and tomorrow. I'm probably going to do extended office hours tomorrow, like a online recitation before the test. So, yeah, stay tuned for information about that. I'll put it on Canvas. Cube. Oh, sorry. All right. Sorry, it took me a little while to get going today. I had some technical difficulties. Thank you very much. Have a good day, and yeah, good luck. Happy studying. Email me if you have questions. Email me if you find errors in anything. Okay. Bye. Okay. Hang up over here first. No. So will the rest of chapter 12 be in physics 2? No. Physics 2 is we just hop right to electricity and magnetism. The parts in chapter 12 that are very different, I think you will see in like dynamics maybe, if you're a mechanical engineer. If you're not a mechanical engineer, it's not that important. Angular momentum, really. So we just never get there. So.